Today's topic, the path to Wi-Fi determinism, from concept to realization. This topic we talked about for many years now is coming to fruition today and will continue to be developed into the near future. So what's the deal about determinism? It's a concept we use a lot in the industry today. 5G for years called this ultra reliable low latency communication, URLC for short. That was a concept that we definitely took upon as a challenge in the Wi-Fi community. And we looked at the use cases with partners like Intel, for example, and Meta, and asked the question of customers, what do you need determinism for? Why do you have to make Wi-Fi better than it already is? Wi-Fi is pretty good. If you join Wi-Fi easily unencumbered with open roaming, for example, the Wi-Fi generally is very, very good today in enterprise and most venues. However, applications don't think the same about Wi-Fi that we do, because applications, for example, in this case, virtual reality, mixed reality, augmented reality, all of the realities, the actual realities, industrial automation use cases, those kind of applications would disagree with your assessment that Wi-Fi is good enough. Because when good enough, it means we, as usual, as average users, getting on the web, downloading content, we're watching YouTube videos, etc. That's all great because those networks have been deployed with your application in mind, okay? And the challenge really is that these new applications we're seeing in enterprise and SB space are very challenging because they have very precise requirements. And the requirements they have are exactly the kind of requirements that haven't been addressed in Wi-Fi so far. Because I look at the, let's say, XR or AR applications, now we digitize things like video and audio. Now the human is now the weakest link, in the sense that if I move my head in that, I vision an XR headset, move my head around in the XR VR space, that motion tracking needs to be reflected in the system rendering my video and audio content, and in real time have real-time control between my audio-video sensors and the rendering function in the cloud or the edge cloud, and generate that content in near real time, okay? And the same with industrial applications and automation. Control systems always require rapid feedback of the change between the input of it changing and the output being computed by the compute platform. And so if these inputs are not delivered to from the sensors to the network, and computing an actual usable outcome in a very tight and very controlled amount of delay. That delay could be anywhere from a millisecond for a industrial control system, or maybe 10 milliseconds for this HMD of your headset. The system fails. Okay, it's not a matter of being good or bad. It's either being binary fail or or not fail. And that's the big difference between typical enterprise apps today. For example, web browsers can take between 10 milliseconds and a second, and you won't know it's the difference between between two web browsers, the experience. But if I say the same thing about XR, if I add a second of delay to my XR feedback loop, now you notice in the XR headset the jittering and all the discontinuity in the video playback. Not very good. You lose immersion. It's a failure. This is very key to get this correct. So there's very, very tight requirements around AR, VR, robotics. And the challenge today is that most networks deployed today for Wi-Fi are deployed on a coverage basis. I guarantee today that here was deployed based on some coverage requirement of salvage RSSI or signal strength. And that's fantastic for most use cases. However, in terms of QoS and things like latency and jitter, things that matter to the new applications in enterprise space, it's hard to predict that traffic load in advance. Because also, if I can predict traffic load down to the millisecond in advance, I can avoid congestion, avoid interference, and avoid any kind of disruption in my video audio playback. But you can't do that in practice. So the other tendency, of course, is to increase the spectrum allocation. If I double the spectrum, double the data rates, double the speed, people think, oh, that makes sense, go better, make all the problems go away. It doesn't make the problems go away because all you're doing is doubling the data rate. You're not managing congestion or interference with other networks. That's a key problem that has to be solved within the Wi-Fi community to guarantee we use the word guarantee kind of loosely, but to mostly guarantee the application gets what it needs from this network in terms of the delay and jitter for the applications. So the new applications of interest are definitely in IoT space, and also think about other sources of interference in the enterprise space as well, maybe in the public space as well, things like peer-to-peer devices. We used to call these MiFis or personal hotspots. Now there's a peer-to-peer communication, to technology around that. But those devices also interfere with enterprise networks as well. If I bring my peer-to-peer device into my enterprise WLAN, IoT doesn't know about that device. I bring my phone in, the phone is paired with some other device. I bring in my Meta headset, it's paired to my laptop. IT doesn't control that connection between that HMD and that laptop. All it controls is that personal or business laptop on my desk. So there's another interference source we have to deal with as well to ensure that we get the systematic determinism across the network, today. So a couple of view graphs to talk about what that really means in terms of the net effect on latency. So we see here the progression of technology, Wi-Fi technology, from Wi-Fi 5 to 6 to 7, and later on Wi-Fi 8. What we're showing here essentially is that as we go from Wi-Fi 5, that's sort of the baseline here. Wi-Fi 5 has absolutely no sense of QoS except for putting traffic into classes and hoping for the best. It's the best effort. Hope for the best. Maybe a video gets the right delay. Maybe it doesn't. No guarantees. Wi-Fi 6E and 6, we have the ability to now schedule the uplink from the station, the handset device, the access point. Now we can control in theory, the congestion and the collision domain in the Wi-Fi space for the very first time. That was a very good version, Wi-Fi 6. We used it in high-density venues to improve capacity. So this venue here, there's 1,000 people in this room. They're all contending with channel access. Without uplink scheduling, with Wi-Fi 6, it'd be total chaos. The experience would suck. That's what we used for Wi-Fi 6 timeframe. Wi-Fi 7, we're using that same schedule technology to actually deliver the right SLA, the right performance to the application. So if I'm wearing my HMD from Meta or whoever, and this HMD requires 50 megabits downlink throughput and 10 milliseconds delay, the application will tell the network that's my requirement. That's my SLA, that's my bound, that's my guarantee I want from you, the access point. And the access point will use that information and then schedule the transmissions to and from that device to ensure that latency is met by the access point. And that's a very key innovation in Wi-Fi 7. Okay? Wi-Fi 7 can also be combined with things for the industrial space, including the 802.11 QBV to improve that even further. So we can get down to the 1 millisecond delay bound with Wi-Fi 7 with some TSN innovation from the industrial space. But generally speaking, most applications in the XR video space are good with, say, the 10 to 15 millisecond boundary or limit. That's good enough for most applications in enterprise space. So it is improving. 7 did make a huge jump in terms of managing delay, and we will see that as it gets rolled out today. Applications are definitely incentivized to use it, because if you are an application that requires a particular requirement for delay or throughput or jitter, use that functionality to get that scheduling for the access point. Okay. So a quick sort of view graph how this works in Wi-Fi 7. So think about, I'm in this room today. We all have laptops that someone over here has a VR or an MR device on their head. Now that VR device amongst 100 users today in Wi-Fi with 6 isn't any more special than the other laptops. Okay, that's a basic problem with Wi-Fi 6. With Wi-Fi 7, that HMD becomes quite special in the sense that it'll tell the network what its requirement is for its video and audio feedback loop. The AP will now preferentially schedule the uplink for that device and downlink as well to ensure that as it's serving all the other users, it gives that particular device more resources to deliver its traffic on time to the server to get the real-time feedback. The other technology with Wi-Fi 7 is a technology that is used to control the other stations in the network. So it's fine to say the access point will go out and effectively, trigger all these other stations, say, hey, you transmit now, you transmit now. That avoids congestion and contention and collisions altogether, except for devices that are not managed in that way by the access point, because within Wi-Fi 6 and 7, the trigger output access is optional. So you have to opt into it. A lot of stations will not opt into it because they don't have a need for real-time traffic. That's understandable. However, what we did find in Wi-Fi 7 is a technique to advertise to those stations that certain time slots are critical. Like every, let's say, a video flow, let's say it's, WebEx, okay? Every 20 milliseconds, the video flow appears from the video system over the wireless LAN to my PC or screen device. Every 20 milliseconds, I know that that frame's going to come. So what this technology will do, this restricted time, R2 as it's called for short, will reserve those time slots over the air so that every 20 milliseconds, every other station in this room will avoid transmitting on that time slot to make sure that WebEx frame is all the way down over the air to my device. That's the way that we deal with the other stations in wireless LAN that are not controlled strictly by the access point in terms of scheduling to meet their delay constraints. That's very key technology. That was effectively adopted in Wi-Fi 7 R2, and now we expect that to become the other sort of linchpin or key to determinism in Wi-Fi 7 to deliver this better latency across the board for very dense environments like this conference room here. Okay, so that's phase one. It's in the market. It's coming soon. You'll see it being deployed very shortly by most of the major vendors who care about having real-time experience for their devices and applications. So phase two. So I mentioned two problems with Wi-Fi 7. One is that in this room here, there's probably about 6 access points, and in all the venues you see maybe 20 access points or 3 access points. And in most high-density venues, conferences, even industrial automation, factory floors, because of the nature of the deployment, all the APs are effectively within line of sight with other APs. That means that they're all co-channel interference. So I guarantee you, on enterprise, if I pick up my phone and walk around and tell my phone, hey, look for all of the networks on the channel I'm on, right? So I join my enterprise network, I choose channel 36, okay? I tell my Wi-Fi scan, hey, scan for channel 36. How many other APs are on that same channel? You'll find, on average, 3 or 4 APs on the same channel I'm on. And that's a conservative, very good case. If you go to a stadium or a conference hall, you'll see the same channel occupied by 100 access points on the same channel. That is a lot of co-channel interference. That means that essentially everything I do in Wi-Fi 7 to the experience fantastic for industrial IoT and XR gets blown away by all the other APs in the environment destroying my delay and jitter characteristics. Now I lose my determinism, I lose the experience, it really sucks. So Wi-Fi 8 solves that problem, or will solve the problem. I should be very clear. Wi-Fi 8 doesn't exist yet. It's 4 years away from the market. But 11BN, which is the IEEE work group, is defining technology today that become multi-AP coordination, or MAP-C for short. Now, multi-AP coordination will solve the problem that I just pointed out. It will ensure that APs over there and APs over there, if they're on the same physical channel, will avoid each other when transmitting those critical flows. So if I know that my HMD requires a packet every 12 milliseconds, right? It will tell that AP over there, oh, by the way, every 12 milliseconds, don't transmit at the same time I am, okay? That's a way of avoiding collisions between access points. That's a very key to achieving this deterministic outcome by ensuring all the APs in my environment are synchronized and avoid each other at the key critical times. Now, some people say, well, isn't that very efficient? We had circuit-based TDMA for years. And that's, it's definitely true, except that you have to be really recognize that the amount of traffic demand from these devices, be it a very small industrial controller in a factory, or even my HMD, is quite modest, right? You can run HMDs on 5 megs or 10 megs throughput. 10 megs is nothing compared to the overall capacity of Wi-Fi. Well, thinking multi-gig Wi-Fi, if you want to serve a 20 megabit circuit with coordinated TDMA, that's not going to impact your capacity whatsoever. So you get the gain of having high Wi-Fi speeds, high Wi-Fi capacity, but also getting at the same time determinism for those applications that require that bounded latency across the board. That's a very key innovation coming in Wi-Fi 7 and Wi-Fi 8 with multi-beam coordination. The other innovation too, it became part of Wi-Fi 7 as well, is that we're trying to think about APs in a general sense. Okay, so there's APs on the ceiling here managed by the infrastructure vendor in this venue, right? But there's also APs that I have in my pocket, right? These iPhones are also mobile APs, right? Soft APs, mobile AP, Wi-Fi Direct calls them something different, but effectively they're APs, okay? So if I walk in this building and I have my personal hotspot running, this hotspot could change the same channel as the network in this room. If it does, that peer-to-peer communication, CT communication is called in 6 gigahertz, that interference could, again, mess up my very nice characteristics for my application that need the low latency. And so Wi-Fi, we're also considering embedding or making the peer-to-peer device a peer of the LAN. Don't think of this peer-to-peer device as an unfriendly actor. Think of this being a friend or a collaborator with the AP network on the ceiling, that enterprise WLAN. If this device here collaborates with the APs on the ceiling, we all win, because now we all know which time slots to avoid and and that will ensure that everyone gets access to the channel at the right time to get the latency and the need for their services. That's very key innovation. So including peer-to-peer devices, as well as other APs on a managed environment in the same scheduling regime, the coordination regime, is very key to achieving this outcome we want for dense venues like this with lots of different device types. Okay, so that's a good sort of summary of the technology. Next. Oh, sorry, wrong button, user error. Okay, okay. All right, so a takeaway. So first of all, applications that we call deterministic are already here in the enterprise environment. It's been actually for a long time. I say we have industrial applications for 20 years, 25 years in Wi-Fi. Okay, and applications like Wi-Fi based AR, VR, even Wi-Fi based surgery, or the applications are still in Wi-Fi today. The challenge has been that they've always required what we call overlay networks. So you go into a factory today, you'll see a Wi-Fi network for IT. You'll see another network for the OT, the engineering team. That could be a technology that's not even Wi-Fi. It could be a private 5G, it could be Wi-Fi again. It's overlay network. It's duplicating everything, duplicating the access points, duplicating the cabling. It's all duplicated to achieve that outcome that they want called determinism. So with Wi-Fi 7 and 8, what we do is we converge the IT, OT domains together. IT, the voice network, as we always have today. The OT teams, operational teams, they will have requirements for their machines, the robots, and they will incorporate the requirements into IT's domain, and then you'll configure and dimension the enterprise Wi-Fi network to accommodate both the classic IT application we're all familiar with, plus the new applications around industrial automation and XR VR that traditionally require dedicated networks by themselves. That convergence is very key from a cost point of view, obviously, but also it simplifies the entire process if we accommodate both application types on the same network at the same time. So this technology, again, it doesn't happen by doubling the capacity. Spectrum doesn't solve it, because all it takes is for my device and your device to transmit at the same time and cause a collision. We both fail. It could be at 1% utilization or 10% or 100% utilization. It doesn't matter what channel utilization is. It could be very high load or load. It's irrelevant. All it means is Eric's device, my device decide to transmit at the same time. Boom, collision, we both lose. This technology avoids those collisions and the problem goes away fundamentally, okay? That protocol level mechanics is required in Wi-Fi 7 to do that. It's coming in Wi-Fi 7, Wi-Fi 7R2 especially. Wi-Fi 8, that's a typo actually, sorry, I should have like I should say Wi-Fi 8 is the next step. Okay, sorry about that. Wi-Fi 8 is the next step in providing the determinism for the multi-AP and the dense scenarios we envision for enterprise and SP. With that, I will hand the control back. Diego.
Thank you, Malcolm. Any questions to Malcolm from anyone? Jim.
So, is there a priority field that tells that my remote surgery gets a higher priority than the ocular vision?
It's a great question, Jim. And so within the Wi-Fi, we've always had a priority field. There's always been what we call a traffic identifier or a TID that said this is voice video versus best effort background data, right? But that's not sufficient for what we're discussing here, because it comes down, for example, this device you have on your head, it has regular audio, video, but it also has that high priority pose information, right? And so the differentiation has to be more granular when it's the device or traffic class. So with Wi-Fi 7 and 8, we use a per flow based priority, right? So based on what flow you have, right? This is your highly critical pose flow from the HMD through the network to the server. That flow is prioritized over other flows, right? That's a more precise way of doing it than just doing, say, that everything in that class, everything on that device is high priority. The robotic application or the surgery application would say, hey, this flow, right? This control system that manages my, my surgical robot that's operating on my patient, that flow is distinguished from other flows by, let's say, IP address, and given very precise SLA terms for that particular flow, okay? Which override everything else in the system, right? Even my YouTube video, WebEx video gets bumped for that flow, right?
Okay. Another question from Ahmed. Yeah, you can bring your question.
This whole multi-IP coordination has been traditionally done as, sorry, thank you. So the multi-IP coordination has been traditionally done within a managed network, so like a controller or something like that. The challenge has always been when something unmanaged as well appears on the network. So how does this solve for that problem of managed, unmanaged coexistence?
That's a great question. Actually, Cisco made a contribution, IEEE, last week on this topic, actually. I don't prop my own team, but it's in discussion with everybody. And the challenge is, most of the time, take use case, like industrial IoT, it's all managed. I walk into a factory, I walk into Amazon warehouse, guess what? They take away your cell phone. Bye-bye cell phone, no more interference. Okay, that's one use case. But the other use cases, like for example, XR devices, in enterprise, casual enterprise environments, yeah, most of the time, as soon as you walk behind that first layer of wall in a building, walk behind that building, it's no more interference. It's really only the traditional spaces between enterprise, managed, unmanaged, the boundary cases, like a shopping mall, right? A shopping mall, the main shopping, like the Sears robot operates a big network, but they have little tiny little shops beside them, little shops, right? So one way of solving that is open roaming. I'll just prop that because all it really requires is that the two networks exchange the SLA they need. Okay, as long as both the managed network knows what it needs in terms of its time slot, say it's every so often requires this much time, and the unmanaged WLAN says, hey, yeah, I don't have the same management domain, but I can exchange with you what my time slots are. Then they can both avoid interference. Now that's sort of I say a courtesy protocol, right? I'm very courteous to you by avoiding your preferred time slots. But that's one way of doing it. Another way of doing it is simply to say, via AIRM, I avoid the unmanaged network altogether, right? Because the application, as I said before, for HMDs is very modest in terms of bandwidth. I think 50 megs is good. I don't require terabytes. You could carve off an entire enterprise channel just for application to require that low latency and put all of the XR devices on that same channel and avoid everything else in the unmanaged space altogether. So two solutions: avoid altogether spectrum management. Number two, IEEE HLBN discussing how we coordinate with those unmanaged devices on a per WLAN basis to ensure we don't step on each other at the wrong time.
Thank you.
Yeah.
Malcolm, thank you so much.
Good to see you, man.
Great presentation.
Thanks.